So good evening to everyone here. So we are here with lecture number 4 on fluid mechanics. So firstly, make sure the screen is visible to you and I'm audible to you. If is it so, then give me a thumbs up or you can put a message in the chat box. Okay. So good evening, Bharat. Good evening, Shiva. How are you? We will wait for 1 or 2 minutes more. Let the others to be joined, and then we will further proceed in the lecture. Okay. Shiva and Bharat, are you there? So make sure the screen is visible to you and I'm audible to you. Okay. Okay. So assume that screen is visible to you and I'm audible to you. So we are here with our lecture number 4 on fluid mechanics. In today's session, what we are going to learn? So we are going to learn about the buoyancy and Archimedes principle about buoyancy. Okay. And firstly, we will know about the term what is a buoyancy and where did it come from. Then we will move further and describe it more in much more detail. And then we will do the Archimedes principle. One of the one topic that we are going to learn is force and torque due to hydrostatic pressure. Then buoyant force and the Archimedes principle and floating conditions. So these three topics we are going to learn today. Okay. So tight your seat belt and let's just get started with it. So firstly, we will deal about the force and torque due to hydrostatic pressure and why we need to discuss it and why we need to calculate it. Hello, Rajesh. How are you? Good evening. So make sure the screen is visible to you and I'm audible to you. Okay. So why do we need to calculate force and torque due to hydrostatic pressure? Because in everyday in practical life, we store the water behind the wall of the dam and we call it a reservoir, water reservoir, which is protected by a wall, vertical wall, which is called as dam. So if you are a civil engineer there, you need to calculate that how much amount of pressure or force the this water has been exerted on the wall of the dam, so that accordingly you will make your calculation and use the concrete and design that dam according to the hydrostatic pressure. Okay. So here you are clear with why we are going to discuss this. Okay. So I have taken an example here. This is a dam or a reservoir of water. You will consider up to this height, the water is being filled in this. Okay, this is all water inside it, and we need to calculate that how much amount of force this liquid is being applied on the wall of the this dam. Okay, so let the height of this water up to which the water has been filled is, let's say, capital H, and the width of the dam is b. B. Okay, and this axis, this is a, you will take as a reference line, and this is termed as O. Okay, and the width is b. So what we are going to do, how we are going to calculate the force? With the help of pressure. So we have considered a point, a line at a distance y from the bottom. Okay, so if I talk about that, what much amount of pressure, how much amount of pressure is being acting on this line? So you will say that the pressure acting on line is rho g. Why? No, because in the calculation of pressure, you have to measure the distances or the depth from the free surface of water. Free surface of water started from here. So this height you will need. This height you will need. If this complete height is h, this is y. So this will become h minus y. Now rho g h minus y you will take here. This is equation number 1. Okay. Now to calculation of the force, you need some kind of area, and you will know that pressure is not constant throughout. It will vary as y will vary. So what we will consider? We will consider a strip of, just a second. We will consider a strip of length dy. The length of this strip will be dy, which means the height. Okay, and the length is b. So this strip is too small, so the force acting on this strip will be so small. So df here is equals to pressure at that particular point into height, sorry, area, dA. So pressure into area will be, this strip is a rectangle of height dy and length b. So this area will be dy into b. Got it? You know the value of pressure initially. So df here will become rho g h minus y into b into dy. Now what you need to do? You need to integrate it from 0 to h. 0 to h. Okay. So for 0 to h, you have to integrate it. 0 to f, you will get the value of s. So this f is equals to integration of 0 to h rho g b h minus y dy. Now this is a simple integration. So f here will be 0 to h. You can take rho g and b as constant because they are constant. Integration of 0 to h minus y dy. Now f is equals to rho g b h dy. Separate the integration 0 to h dy minus 0 to h y dy. Got it? Just give me 10 seconds. Just a second. Sorry for the disturbance. Now, this integration will lead you to F is equals to, and thanks for the patience of your guys. F is equals to rho GB. Now, H dy will become H into this integration 0 to H. Dy will become H minus 0. Because we know that integration 0 to X or 0 to A dx will become X 0 to A, and which results in A minus 0. Okay. So it is plus one term more extra we have, minus integration of y dy will become y square by 2, and limits are 0 to h. Now this will become 1 by 2 times rho gb h square by 2, and that 2 I have taken common. So it will become f is equals to half of rho gb h square, because this will become h square by 2. So rho gb h square minus rho gb h square by 2. 1 minus half will become half. So this is the total force. This is total force that is acting on the wall of the dam. Now we will talk about the torque. So in the same equation, we know that this is the case. Up to this height, we have filled the liquid of water, which is H, and this width is B. We have considered a strip here of thickness dy. Now we know that torque is nothing but force into perpendicular distance, or F cross R, but magnitude, in magnitude it will be F into R, perpendicular. So for this small strip, we are going to calculate the small torque, because torque will depend on force, and force is variable here, because we know that force is 1 by, this is the total force, but to calculate this total force we have to integrate this, because pressure here is varying. So that is why we have to calculate small torque. D tau is equals to about this axis. Let's say this axis is O. So this, on this strip, the water will want to be come out. So it will apply a constant, it will apply a torque like this. So this is the gate of the dam. So water want to fill out like this. So it want to rotate the gate like this about this axis. Okay. Now that is why the torque has been developed here. So we have calculated the torque about this line. So the perpendicular distance is this, which is y. So it will become df, the amount of force applied by this strip, into perpendicular distance, which is y, because f is in outward direction, df. Now d tau is equals to df. The value of df we already know, which is, it is p dy b. P dy b into y. So d tau will become pb y dy. Now we know the value of p. The value of p is nothing but is equals to rho g h minus y into b y dy. So again we need to integrate it from 0 to h, 0 to h, because the length, this y varies from 0 about this line to h. The maximum height up to which the water has been filled in this. So you calculate the torque, it will came out as 1 by 6 times rho g be h cube. So this is the total torque. It is the total torque that we need to be countered by the gates that we put in front of the dam, because water is applying that much amount of torque. So we have to counteract it. This is the total torque applied by water. Now, we know the expression of total force. We know the expression of total torque. So what we are going to do, we are going to do, we are going to find out the line of action of that total force, up to which height we should place the gates. Okay. So let the height will be h dash. So the total force will be acting here will be, the total force is 1 by 2 rho gb h square. So on that height, this total force will produce the same torque that is produced by the total amount of water. So F total multiply by H dash, it is the torque produced by this total force, and I am equating it with the total torque, which is rho GB into HQ. Put the value of F, it is rho GB H square by 2 into H dash 1 by 6 rho GB HQ. Hi Shravani, how are you? So rho GB and rho GB will cancel out. H square will cancel out the one of the 2 of the power of it. H dash will become here 1 by 3 times of H, which means line of action of this total force is about, this is the dam and this is the total height H. So line of action of this force will pass out. We are measuring the distance from here. Okay. So from here it is H by 3, and from the upside it will be 2H by 3. Okay. And that is why if you will, if you have ever observed a dam, so the wall of the dam you will see in the back side, they will like this. Why it is so? Why we have maintained this? Or you will see it like this. As you move down in the dam, the thickness of the wall has been increased. Why it is so? Because as you go deeper and deeper in the water will exert more pressure on the wall. Because we know that pressure inside a liquid is nothing but rho g h, which depend on the depth. So as the depth increases, the pressure of the liquid increases. So it will exert more force in the downside. So that is why we made the downer side of the dam thicker than the upper side, so that we counteract that pressure. Got it? And to compensate this torque, if you are constructing a dam and you put a flat face, okay, so what will happen? You have to secure that flat face, because the water behind it, the water behind it will apply the torque, and which is exactly equals to this. So what we are going to do, instead of making it a flat face, we make it a semi-cylindrical face, so that the force which is acting on it will pass at the center of it, and the net torque will become zero about this point. Got it? Now, now the buoyant force we are talking about. Now, what is a buoyant force? See in this example, you will generally observe when you put a bottle inside the water, it will float on the surface of water. Some of the crazy minds will do, they will sink that bottle in the water and left it there. But what will happen? The bottle will come up in the emanation. You will see how is this happening. What is the mysterious force that is working behind it? Which means if the bottle is going taking itself to the upside of the liquid and not floating inside it, which means there is some force acting on the bottle, है ना? And that force must be exerted by the liquid because there is no one else to exert the force. So the force exerted by the liquid on the object we placed on it is termed as the buoyant force. That force is nothing but the buoyant force. Okay. So buoyant force is the force exerted by the liquid. Okay. Now, in the fluid, weight is generally given by, we talk about the fluid. So weight is mass into gravitational acceleration. Mass is nothing but density into volume into G. So in liquid, in the case of liquid, we generally interested in the volume and density. So we will not consider M, we will consider rho Vg, the weight of fluid. Okay. Now, this is the sphere we have taken. Now, if we take it outside, this much amount of liquid, it has filled inside it. Okay. And this is rho of liquid G into volume of this sphere. Now, in this sphere, this surrounding liquid will exert a pressure. We know that uniformly. Okay. So this will result in a net force which is acting upward in the upward direction. And that force is due to remaining water. Got it? If you take this is the liquid bowl. Okay, we have just imagined it, but this is the proper solid bowl we have taken. So the weight of it will be rho of solid, density of solid, gravity into volume. If we drop it in inside the liquid, it must have displaced the some amount of the liquid because it is solid. So liquid cannot fill inside it. Okay. And that much amount of the water, that much volume of the water will be displaced by this solid, and the remaining portion of the water will exert a force on this ball. The resultant of these forces will be in upward direction. Okay, will be in upward direction. Force due to remaining water. Okay, this force is termed as the buoyant force. Now, whenever a body is submerged partially or fully, either it is partially or it is completely submerged in the liquid. Okay, so it always experiences a net upward force, and this upward force is termed as the buoyant force, and this phenomena is termed as buoyancy. So you have imagined it. If there is a tube well around you, so when we fill up the water from that with the bucket, with the help of bucket, so when you are trying to grab the water and lift that bucket of water, it will feel very, it will not feel you very heavy when, until it remains in contact with the water. And why it is so? Because of the buoyancy of water. Okay, when you also taking a swim or bath inside a swimming pool or the tube well jacket, so we will also experience a force, because if you take a dip inside the water, then water will float you up. That force, that property of water to exert a force is termed as buoyant force. You will see, if there is a liquid and we have considered an object on, So this portion of the liquid will exert a pressure which is uniform in nature and radially inward. Why it is so? Because this water want to come inside, want to fill this space. If you take this portion, half of the portion, this will have a component, this will have a component in this direction and perpendicular direction. This will also have a component in this direction and perpendicular direction. But on this side, if you will see, they have a component in this direction and perpendicular direction. So this component and this component of the pressure will be cancelled out. So the net force that you have in the upward direction. You can also say that, sir, this component which is acting upper side in the upper half, this component has a component in the downside. Yeah, obviously. So it will cancel out the upward component of the downside. No, because this component is because of the pressure, and as the height increases, the pressure will increase. So this component on the downside has more magnitude than this side. So they will not cancel out each other. The net resultant force you will have in the upward direction. Now I think you are clear with the concept of this buoyant force. So buoyant force, simply you have to remember, buoyant force is exerted by the liquid with the sufficient pressure difference. Okay. And it is upward in direction always. Now, so generally the buoyant force can be calculated as F buoyant is equals to density of the liquid, gravity into volume of the body displaced, or you can say volume of the body that is submerged. Got it? So for example, how this come? Suppose this is the bucket full of water and we have take a cylinder inside it of length A and base area capital A, and length should be L. Okay, so the pressure acting on this surface will be P1, and let's say the pressure acting on this face will be P2. So we know that P1 minus P2, or you will write it as P2 minus P1, is nothing but rho GH, and rho is taken as of liquid. So rho GH, and H here is nothing but L is the length of this cylinder. Now we know that if you talk about the force, so it is F2 into area minus F1 into area, so rho G L. So F2 minus F1 is nothing but rho G L over A. Okay. Now you will see that there is a weight of the liquid which is acting downward, which is exactly equals to mg, mass of the liquid, and volume of the, you will see it, rho into volume into g. This is the weight of this cylinder which is acting downward in the downward direction. To compensate that, we will have a pressure difference rho gl upon A. Okay, so what we can do, we can equate these forces F2 minus F1 with the mass, which is rho g into V. This V here is the volume of this cylinder we have taken. So it is the submerged volume of the cylinder. Got it? Now, so The buoyant force will depends on the density of liquid, that the liquid is dense or rare, and volume of the body that is submerged in the liquid. Okay. Now, or the another formula that you can use is volume of the density of the liquid, gravity into volume of the liquid displaced. Now, if a body weight W in the air, then what will happen to its weight when it is dipped into the water? Now, suppose this is the body having a weight W in the air, and we have dipped this body in the water. So what will happen? The water will exert the buoyant force on this body in the upward direction. Just a second. So water will exert a force in this body, on this body in upward direction. This is FB. So the net resultant weight of this body will be given by FB minus weight. So this is called as the apparent weight. The weight that we feel inside the liquid. This is the apparent weight. Now force of buoyancy, we know that density of the liquid, gravity into the volume that is inside the liquid. So we know that in this case the complete volume is immersed in the liquid. So we will take it as V minus weight of the liquid. So density of the solid into gravity. The complete volume is inside. Okay. So here you can see that it is, you can take this G and V as common. So it is rho of liquid minus rho of solid. Okay. Now, according to this question, so weight minus FB, which is the buoyant force, I have. So in this question, the net weight or the apparent weight of this object will be W minus FB or FB minus W, depending on the densities. Okay. Now, does the air apply the buoyant force? Think about it. Air can also apply the buoyant force? Yes, of course, because the buoyant force is a property of fluid. And we have seen in the previous lecture that air is also a fluid. So this is possible that air can also apply a buoyant force, although the magnitude of that buoyant force which is applied by the air is very low. Why? Because in buoyant force, the density of liquid must be there, or density of the fluid, I will say. The air has a very low density. So that is why the amount of buoyant force that is exert on the bodies will be very low. And this is nothing but the air resistance that we feel. Okay. Now, okay. So because of very small density of air, it applies a negligible amount of buoyant force because of the density of it. Suppose the air is become same denser as water, so it will also apply the buoyant force on you. Okay, got it? Then if you are not denser than air, you will also start floating in the air. Got it? So in this question, we will come up with a question here. So a block is given with a density of 600 kg per meter cube, which has a dimension as shown in the figure. Okay. If its half portion is submerged in liquid of density 900 kilogram per meter cube, then calculate the buoyant force applied by the liquid. Now, it is given in the question that half of its portion is submerged in the liquid. So liquid is filled up with the 2 centimeter height because it is 4 centimeter. So half portion के लिए we have to fill the liquid up to 2 centimeter height. Okay. Now, we know that buoyant force is only applied to that volume which is immersed inside the liquid. Suppose you have a bowl and you have a bucket of liquid water. If you do not put that put that ball inside that liquid, will you feel any kind of buoyant force? No. So until and unless the body is submerged, the body is made the contact with the liquid, there is no buoyant force. So for buoyant force, the contact of the liquid and the particular body, particular material has to be made. Okay. So here, this object is submerged inside this liquid up to the half portion. Now we know that buoyant force is nothing but buoyant force is nothing but rho, density of liquid, gravity into volume of the liquid, volume of the body immersed, volume immersed. Okay. Now you can check that this much amount of the volume is being immersed. This is a cuboid of height 2 centimeter, length 5 centimeter, and width 5 centimeter. This much of the volume is submerged inside the liquid. So volume immersed will be volume immersed equals to 2 into 5 into 5, which is 5 5 to 25, 25 to the 50 centimeter cube, or you can convert the centimeter into meter. So it will be 10 raised to power minus 6 meter cube. This is the volume immersed. Now we can calculate the force of buoyancy. Rho of liquid is given in the question, which is 900 kilogram per meter cube. Okay. Hello Shamila, how are you? So volume immersed we have already calculated. G we have to take in as 10. Volume immersed here is how much volume is immersed in the inside the liquid? It is 50 into 10 raised to the power minus 6. 50 into 10 raised to the power minus 6 meter cube. Now calculate this. So it will become 45 into 1010 are there, 40. They will cancel out the 4. So it will become 10 raised to the power minus 2. Or you can say it is 0.45 Newton. It is the buoyant force. So this much amount of the force will be faced by this block. Okay, this is the buoyant force that is applied by the liquid. Okay. Got it? Now, Archimedes principle and condition of floating. Now, Archimedes, one of a famous Greek inventor, scientist, engineer, and physicist and astronomer. Okay. So let me tell you one thing. You will see this video. This is the 5 kg weight inside the liquid, and you will measure it in the first case with the help of this measurable device. So it will exactly tell you that it is 5 kg. Now in second case, this is a pot of water. Okay. And we have made the hole exactly at the level. We will put this 5 kg weight inside that pot. So it will displace some amount of water because it will create the cavity. The water cannot fill inside. So the level of the water will rise and it fall through this. So this is the amount of displaced water with this weight. Okay. Now you clear with the displaced water, how it is displacing water. The weight we put inside the liquid level will rise, but we have made a hole exactly at the level of the height. So the amount of excess liquid or the liquid displaced by this weight will be covered in this. Okay, will be collected by this pot. Now, what does Archimedes observe? Archimedes, I will tell you a story about this. Archimedes was live when there is a ruler of name Haya. Okay. Haya second. So Haya second has made has ordered the goldsmith to made a crown for him. He made the crown, but that king Haya second was not believed in that on that goldsmith. He was no. He knew that that goldsmith is not honest, is dishonest person. So he definitely made some impurities in the crown. So he want to check that whether it is made of pure gold or it is infused with some impurity. So based on that, he know that the very famous physicist, scientist, inventor is there in his country. So he called Archimedes and put the throne in his hand and said that you need to calculate that is this made of pure gold or not, but the condition is that you don't have the access to destroy it or to melt it. So without melting, without destroying, you need to calculate the density of it. Sorry, you need to calculate the density, because on the level of density, based on the density, you are going to say if the density matches with the density of gold, then you will see the this is made of pure gold. So Archimedes think of it day by day, day by day. As the day passes, one day Archimedes going to take the bath. So when he came down on his bathtub and take the bath, so when he cover itself with the water inside the bathtub, when he go inside the bathtub, the level of the liquid, level of the water will rise, and suddenly there is a spark in the mind of Archimedes that if I am sitting inside a liquid, the liquid will rise up, which means the same amount of volume, because volume remains constant. So what is my volume? I have displaced the same volume of the water outside the liquid, outside that tub. Okay. And this will get a spark in his mind. He put the gold crown in a pot of water and calculate the amount of water displaced. Based on the volume of that, he will able to calculate the density of that gold. Okay. Because he know the mass of that, he know the mass of that volume displaced. Volume mass is nothing but density into volume. The density of gold into volume of gold is equals to density of that liquid into volume of that liquid displaced. So he put the density of gold into volume of the liquid displaced, because both are same. The volume of that crown and what he has displaced, that would be same. And because of that, the density will become out, and density obviously is lesser than the density of gold. So the dishonesty of that goldsmith will be proven by Archimedes without destroying, without melting that. And this is we know as the Archimedes principle. Now we will talk about the Archimedes principle. He is the great scientist, I must say. So when you put this 5 kg pot inside the liquid, the apparent weight would be different. And let's say the apparent weight of this object is 2 kg. So it will displace the same amount of water inside the outside of it. Okay. You will see in the dial it is showing 3 kg, and inside it it will become 2 kg. Got it? Now, which means if it is measuring 3 kg inside the liquid, which means 2 kg is the buoyant force, and buoyant force is nothing but the rho of liquid g into volume immersed, which means this much amount of volume has been displaced, and rho of liquid and volume immersed is nothing but mass. Okay, so this much amount of mass has been displaced. Got it? Now, because the total weight is 5 kg, we know that 5 kg. The the reading after we dip this inside the liquid is 3 kg. So if we take the difference of it, 2 kg will be there. This is the apparent weight, 3 kg. So which means 2 kg has been displaced. So this is the displaced water. Now, so Archimedes' principle says that state that whenever a body is fully or partially submerged inside a liquid, it experiences a net upward force, which is a buoyant force, which is equals to the weight of the liquid displaced. Okay, so it will exactly displace that much amount of liquid, which force that it has been experiences. Okay, so it is displays the same amount of liquid which is equals to the buoyant force, the weight I am saying. Okay, and weight is a force. Now, why would the wood float and pin sink? Because of the density difference. Because density of wood is less than the density of water. So, upthrust, we know that upthrust over the buoyant force is nothing but rho of liquid g into volume of the body immersed. If the rho of liquid and weight of the body is nothing but density of the body, gravity into volume of the body immersed. Now, if the density of body is greater than the density of liquid, then what will happen? Then what will happen? This expression weight of the body will be greater and the weight float, this buoyant force is less. So we can say that buoyant force is less than the weight, so it will sink. What it's because there is no sufficient amount of upward force to hold this. Now, you will see in this, if the density of the liquid is 0.1 gram per centimeter cube, this much amount of the liquid is being displaced. As the density increases of this block, this is the density of this block. As the density decreases, the volume displaced by this object is being increased. Got it? Now, so generally, if density of the liquid is less than density of object, the object will sink. And if the density of liquid is greater than or equals to the density of object, then object will float. Condition of floating is when the buoyant force is equals to the weight of the object. Now, why does a duck float in the water? Because of its biological function. So what is happening there? The duck's feather help them to float. They repel the water. Okay, like we have seen in the boat. Okay, there are blades now which throw the water backside, so then we can move in the front side. Okay, in the forward direction. So the weather, sorry, the feather of the ducks will also not only help to push the water backside so that it can move forward. This feather, what they will do, they will trap the air inside him. And air is rarer than water. So air will not sink in the liquid. What will happen? So this the feather have tiny barbs which allow them to latch together like velcro. Okay, But this creates a balloon-like effect, trapping air in between feather and the skin, and those air bubble add to the duck's natural buoyancy. Okay, because of that air trapped in that feather, the duck will able to float on the water surface. Now, a block of wood with the dimension 0.12 meter, 0.34 meter, 0.43 meter float along a river with the biggest face facing down. The wood is submerged to a height of 0.53 meter. Now, what is the mass of the piece of wood? Very simple question. The biggest face is submerged, like this one is submerged. Okay. So the cross-sectional area here is 0.43 into 34. So it is 0.1462 meters square. Now, the weight which is acting, this mg is the weight of this wooden block, but it is countered by the buoyancy force, and which is because of this volume immersed inside this liquid. Okay, this is the buoyant force, and we know the condition of floating because it is not sinking inside it, which means it is floating. So for floating, this buoyant force should be equals to this weight. Now, buoyant force is equals to the weight of body. Buoyant force given by density of liquid, gravity into volume submerged. Volume submerged here is this much, 0.53 into this area. This area multiplied by this height, and density of liquid is given as, so it is water. So generally we should know about the density of water, which is 1000 kilogram per meter cube. Okay. Now, so water, the mass here will be 7.75 kilogram. Okay. So this is it from my side. We have covered the floating condition and Archimedes principle, and also we have covered the force and total torque by the hydrostatic pressure. So in that, till now, if you have any kind of doubt, you can ask. You can put that doubt in the chat box also. Okay. And if not, the lecture is been over. Thank you so much for being attentive in the lecture. Okay. Keep studying. Try to ask question about the concept. Okay. And be attentive and be responsive. Okay. Thank you so much.